So we're going to make a makeshift monochromator, and before we do that we should understand what a monochromator is and why it's used and what we're going to do different. And so monochromator is an optical instrument that can very effectively pick out a very narrow range of wavelengths, so you can effectively get one wavelength out. And they're used for studying properties of material that are dependent on wavelength. There's two main different types of monochromators. There's those that use diffraction gratings and those that use prisms. The diffraction grating monochromators can be, just use diffraction, and they use a diffraction grating clearly, and it's described by this relation here we've seen before. That's the gradient equation. M lambda is equal to d sine alpha plus sine beta. And more importantly is if you invert this equation, you can see that the angle to which light reflects off the diffraction grating depends on its wavelength, and it's inverse sine or something like that. And so with that, a common setup is something called the Chemi-Turner monochromator, and how it works is you have a light source, there's a beam that comes in, it hits a collimating mirror, and it comes out and hits a diffraction grating that can importantly rotate very precisely. You have to have very fine rotations, and we'll see why later. And then you have the light beam diffract off of this reflective diffraction grating, hit a planar mirror, and come out an exit slit to some detector. And again, the importance is that this can rotate, the diffraction grating can rotate very precisely so that we can, again, get whatever diffraction order, typically the first, to get out the exit slit. And the diffraction order will correspond to some spectrum of the incoming or of the light source. The other kind is called a prism monochromator, and as the name implies, it uses a prism. And it's a very similar setup to this. It's a little different in the geometry. However, it's described by Snell's law, which we all know. And Snell's law, the index of refraction is dependent on wavelength. And so different wavelengths of light will refract at larger or smaller angles, and so we can use that to our advantage to pick out a small band of wavelengths. And so, again, a common setup is you've got a light source, and then you've got another prism that rotates finely, just like over here, and then we've got a focusing mirror that focuses it out of an exit slit into some detector. For our purposes, our detector will be a CCD on an iPhone. The problem with these kinds of monochromators is they're very good for scientific research. And that doesn't sound like a problem, but there might be applications where we don't need such high precision as we have with the Chemi-Turner and these prism monochromators. And the practical kind of disadvantages to these are they're very, very expensive. Can be tens of thousands of dollars, especially the Chemi-Turner monochromator. And it's all because of they're used for scientific research, and they need to be this precise. I mean, the diffraction grating has to be milled very fine. It has to be put on a very heavy and very bulky housing so that there's no light pollution and all that kind of stuff. And that's all well and good for scientific research, but if we want something a little bit less precise, we can build a monochromator that's serviceable for something that you only want to differentiate between general color for far, far less. And if we come over here, we'll see what we've done. So over here, we've got our Lego monochromator. The housing is Lego only. We have some electrical tape out front to block some of the light pollution, but considering this is all Lego, there is going to be some inherent light pollution. And in front, inside, you can see there's a prism on a rotating platform that corresponds to the rotation of a dial over here. We've got a model of this setup here. It's a worm screw, and then a platform, and then a knob, and then 70 turns of this knob correspond to 1 turn of this platform. So again, we can very finely rotate this platform to get the prism at such an angle that we want. Calibration, we'll use laser light. So we'll use laser light incoming here, and then it'll hit the prism and diffract onto the CCD. And using that, we can use the RGB value of this of the laser light and check it against the reading on this dial here. And so we have to use the RGB value from here, and then we can check it from somewhere else. Excuse me. The experimental setup will be white light. We'll have a white light source here. Let me again incoming to the slit, and then out the other end will be CCD. And we scan across this range from about a visible light, so from 400 to 700 nanometers, and take many different points. And again, compare the RGB values of the points here, or on the CCD, the images on the CCD, to the known RGB values of the wavelengths that we're trying to pick out. And so we do that, and the way that we do that is, just RGB analysis. We take the difference of the two, of the one that's on the image and the one that we know it is. We take the difference and we can do error analysis. And we've done that with about 10 points, and our conclusions are that this is a pretty good setup if you want differentiation just between general color. It's not terribly good at being very fine, being able to select a particular wavelength. The Chemi-Turner, these prism monochromators, are precise within 1/10 of a nanometer. And it's almost obvious to see that a construction made of Legos, electrical tape, and a prism that costs $6 isn't going to be able to have that kind of precision. However, there are several applications that don't require that kind of precision. And so this is a model, and it works just fine to differentiate general color. Some potential improvements that we could do is obviously we could black out the inside of this a little bit more. Legos are a little bit reflective, as it turns out, and the reflection of the light off the Lego bricks mess with the intensity of the light that we get on the image, and the intensity of the light affects the RGB values of the image, and so that disrupts our error calculation a little bit. But besides that, this is a pretty okay model for this kind of stuff. It's again very cheap. It's made out of Legos, $6 prism, some electrical tape, and a 3D printed mechanism, and that's all you really need for this kind of application.